Okay, so I think that our center produces all the devices in plastic, thermal plastics, and using this replication techniques. So I think my talk will mainly consist of two parts. So I will just briefly give an introduction of different molding-based technology. And then I think I will just give some fundamental limitations and practical guide to achieve the successful molding. So molding, I think everyone knows what molding is, right? I think everyone did this, have ever made waffles, right? So basically molding is nothing different from making waffles. What you need to make a dough, right? You need to have a mold, right? And then you need to also make a dough, and you pour dough into the molds, and then you close the mold, and then you heat, and then after that, your dough will become hardened, and then you remove, and then you eat, right? So basically, what the important parameters for molding. So mold itself is important. Sometimes we call stem, sometimes we call the mold, and then now normally what do you do on the mold surface? You put oil, right, to prevent stiction. So for surface coating is important, and then also this tool itself is important, and then you need to control. Also, once you put dough, then how the dough will flow to fill into the gaps in this mold structure is important. This is a polymer rheology, right? And then now you need to optimize the process, temperature and pressure and time, right? And then once you have this the waffles, then also you want to if you want to sell these waffles, I think basically the scaling up is a very important issue. Okay, so now so this is also one example of the micro and nanoscale molded commercial products. The compact disc is basically microstructures, so sub-microstructure, and DVD or Blu-ray disc is basically even smaller structures you can easily find, right? So there are actually different molding techniques. Okay, so hot embossing or nano imprint lithography is one thing, and injection molding. Okay, I think these two are mostly they are available at KU, LSU, and also many universities. And also, Dr. Matt Hooper already talked about the PDMS casting or soft lithography. And also these days, also people try to make a lot of devices using roll embossing, but I will mostly talk about these two techniques. Okay, but what is needed for replication? Oh, we need molds or stamp, right? So actually, in the first part of today's morning section, we talk about a lot of techniques to produce micro and nanostructure. We can use any techniques, okay, to make a mold. So I will not talk about that, okay? But the reason why we introduced the micro and nano patterning method in the previous section was because we need them to produce molds for our center application. Okay, and once we have like some molds or the molded structures, what you can do. So one example is once we have this molded, So how we can make a mold? So we can make some microstructures using either photolithography or micro milling, and then also based on that, using that as template, we can do electroforming, and then basically we do the overplating, and then we can make a mold insert, and we use this for molding into plastics. Okay. So the first, I'll talk about hot embossing. Okay. So hot embossing, you need a substrate. Here, normally you use a thermal plastics, okay? And we place between two platens here. But on top of one platen, we put mold insert, okay? And then we increase the temperature, and then we apply force. And then what happens? This polymer of the substrate will go into the cavities of mold structures. And once it is filled, then we cool down and we remove. And then we demold, and then we have the negative patterns from the mold insert in our thermoplastic substrate. Okay, so this is the Hex 03 machine. I think this is the kind of best machine existing in the world, but they're not producing this machine anymore. But I know that KU has just acquired that, and they are now assembling the system. So that is the So just if you look at that, you can place the mold inserts on here, and then substrate, and then we put them together, okay, and then we apply heat, and then pressure, and then remove, and then you get this replication. Okay, so nano imprint lithography is very similar to hard embossing. Okay, but some people say they're the same, but some people try to differentiate these two processes. But main difference is for nano imprint process, because we have nanoscale structures, we make patterns only on the top surface of your substrate. So that's why they say it's imprint. Okay, but process itself is the same. We think of polymer. We can also use thermoplastic bulk material, and you have a stamp or mold, and then you increase the temperature above TG, and you apply pressure, and then you cool down below the TG of the resist material, so that this part becomes hardened again, and then now you separate mold or stamp from the molded substrate. So basically, we have demolding. And all the important issue to achieve nanoscale patterns, okay, nano molding or nano imprinted lithography is nothing more than it's exactly the same as to make waffles. So to have a good resist is one thing, to make a stamp. Also, you need to put anti-sticking layer on the stamp surface as you put oil on the waffle fabrication. Okay, and then now you need to control the process, temperature, pressure, and time. I will discuss later in more detail, and that will determine how resist flows. And then now you need to find the application what you want to do with the pattern structures. Okay, so one example. This is kind of the first of the results that was reported to make nanoscale patterns using this nano imprinted lithography from the group of Princeton University by Dr. Stefan Zhu. Okay, so basically they use the molds made in silicon oxide and to produce to replicate the patterns into PMMA. Okay, and then into this hole they deposit metal, and then they removed PMMA so that they did the litho process to produce metal dot structures. Okay, so this is kind of the initial work on nano imprinted lithography. There are some nano imprinted derivatives. Okay, so normally for nano imprinted lithography, you need to increase the temperature, but they also developed so-called room temperature imprinting. What they did was they just exposed your substrate into the solvent vapor. So what does this do? You partially melt the top surface of your substrate. Okay, so you don't need to increase the temperature while the polymers at the top surface is still mobile, and then you imprint. Okay, and these days, a lot of people are using so-called UV imprinted lithography. Okay, so instead of using thermoplastic, you use very flowable UV resin. Okay, and then the important thing is your stamp should be transparent. Okay, so now you put UV resin, you apply pressure, and then now you shine UV so that UV resin becomes cured, cross-linked, hardened. After hardened, you demold, and then now you have nano patterns. Okay, and the Princeton group also developed a technique to direct nano imprint into silicon material. All the previous examples, they made the patterns in thin plastic material, but here what they did was they just used excimer laser. Okay, they shine excimer lasers through the transparent stamp. What it does, it briefly melts the top surface of a silicon layer, and then they imprint it. And then they demonstrated the nano patterning using this method. They call this laser-assisted direct imprint. So the next process we want to discuss is injection molding. Okay, so it injects. So I think this afternoon you will see injection molding process during the workshop. So basically, so we put mold here. Okay, and then now what we are doing is here we have a hopper here, and we put plastic granules. Okay, and then here we have screws. So, and the screw moves, and then here heater. While heating, so we melt the plastic granules. Okay, this screw will bring the molten polymer into the mold cavities. Okay, and then now you fill the mold cavities, and then you do the molding. So this is just one video doing this injection molding process. So when you cannot see a lot of things, but when it's separated, I think you can see the molding part was mostly fast. Right? So what I would say is it's so fast. Okay, so depending on the structures and materials, but you can make one part within like a seconds or sometimes within a minute. And there are also some injection molding derivatives. Okay, and what KU has is injection compression molding. Okay, so this is the injection, very same as injection molding. So you inject the polymer, molten polymer through this hole here, but at the same time you compress so that it fills the mold cavity in a more efficient way. Okay, and this is actually injection compression molding. And also there are also many other injection molding variations. Another example is kind of reaction injection molding. So you just put like a polymer components, and then now you mix, and then now you have a kind of polymerization reactions through during this injection molding process. So you can produce you can use different types of materials for that. Okay, this is one example of the nanostructures produced by the injection molding. So they made, this is a kind of Gutenberg fiber, and they made this mold using electron beam lithography. Okay, and then they use this as a mold, and then they replicate that into polycarbonate. Okay, so the molding, why replication is interesting? Because replication can cover very large area of the length scale, from macro scale to like a nanoscale. Okay. So now, I'll just briefly talk about some fundamental limitation and practical guidance for a successful molding process. Okay. So again, what is the important thing? First of all, for all techniques, either nanoimprint lithography, hot embossing, or injection molding, we need master or stamp or molds. We need to make it. I will not talk about this one. And another thing is we need to fill the plastics into the mold completely. Okay, that is also very important thing. And another thing is we need to avoid the distortion of feature, but that occurs mostly for like PDMS casting or soft lithography. Okay, and then also for many cases we have kind of swelling issue. Okay, and also that is a kind of limitation for soft lithography, or also solvent assisted nanoimprint lithography technique. So I'll just skip this part. So now we want to make patterns in plastics. So we have to understand some the polymer properties. So most of the polymer materials to mold is amorphous polymers. Okay, it's not crystallized. It's not crystalline, it's amorphous polymers. So now, from the room temperature, basically, if you increase the temperature, what happens is, first you will have a TG, it's called glass transition temperature. And above this temperature, basically, what happens is this polymer chain becomes a little bit mobile. Okay, so if you have a PET bottle and if you kind of you use a lighter, try to heat, then basically it's not melt, but it becomes mobile, sticky, right? So that is kind of you can say the state above the glass transition temperature. And then so now once you increase the temperature further, then you have melting temperature. Okay, and then if you increase temperature further, and if the temperature reaches about 500 degrees Celsius, most polymers decompose. Okay, now what temperature we need for molding? Okay, so for nanoimprint lithography, or so basically pressing, hot embossing, or extrusion, or rolling, normally we need just polymer to flow, plastically flow. Okay, so we use a temperature between TG and melting temperature. While for injection molding, we need to increase the temperature above the melting temperature of these amorphous polymers. Okay, so this is the temperature range to apply for replication. So now let's briefly think about the limitations, the resolution limitations. So for thermal molding, so this represents a single polymer chain. Okay, and then now, so basically A is the length of each repeating unit of polymers. Okay, and then now R square, this one is basically RMS end-to-end distance, means from here to here. Okay, and S is basically this standard deviation. So that is basically radius of gyration. Okay, basically radius of gyration determines the minimum size of patterns you can reliably pattern using thermal imprinting or injection molding process. And now, for example, if you have a PMMA and you have two different molecular weight, 25K, 950K, and then, oops, sorry. Okay, then basically the radius of gyration for 25K PMMA is around 2 nanometers, and 950K PMMA is around 8.4 nanometers. And that limits the smallest feature size that you can produce using a thermal molding. But when it is talking about like a UV nanoimprinted lithography, because for UV nanoimprinted lithography, we use UV resin, whose molecular size is really small. Okay, so I will not really discuss it in details, but basically for UV resin, there's basically no limitations. So that step is the step from the molded structures by the UV imprinted lithography. And then basically there's no limitation in terms of the feature size that you can produce by UV nanoimprinted lithography. Okay, so now, how many minutes do we have? A couple more minutes. Okay, so there are some practical rules, okay, to improve filling of resist into a mold cavities. So now let's compare these two patterns. This is a mold patterns, okay? Which one do you think will fill faster? Okay, this is a mold insert step. You have a press substrate should be on the bottom. Now, if you apply pressure, which one will fill first? The first one or second one? Okay, so the answer is the second one. Why? Because in order to fill this cavity, basically when you press, then polymer will squeeze in. So all the polymer on this area will squeeze in order to fill this structure. However, in this case, only the polymer to fill into a certain cavity is very close to the mold cavity. So polymer can travel only the small distance. So normally you want to have that kind of structure over this one to have a fast molding. Okay, so if this is your desired structure to produce, what you want to do, you can add some auxiliary structures to enhance the filling of your molding. Okay, and another like a downside is if you have like inhomogeneously distributed structures. So here you have a dense structure. There's no structure here, right? Then what happens is here again it will fill faster, and then this part. So if you use a very thick mold and a very thick substrate, I think it should be okay. But if you use a very thin resist layer, and then if you use a silicone as a stamp, what happens is the sinking time will be different, so that ultimately the thickness of a residual layer will be inhomogeneous over the area, which may produce some defects in the final molding structures. Okay, and for silicone molds, okay, or for animals, you need to put so-called anti-adhesive coatings. And this is the molecule which is mostly used for like a silicon step. Okay, so you basically make your surface hydrophobic, okay, so that it will not stick to the substrate. That's one example of, so I'll just skip this one. And one very important thing, I'm in mechanical engineering department, and you are chemistry, you're in chemistry, right? And what I like in basic sciences is you are very keen to cleanness, while most of the engineers are not, because we are used to very dirty process. So when I have a new like graduate students, the first thing I try to teach is you should keep everything clean. Any single dust will ruin your process. Okay, so that applies for any micro and nano fabrication techniques. Okay, so very, very important to have an environment without any dust. Okay, and basically, if you put a very good anti-adhesive coating layer, that will not only improve the demolding process, but also it will reduce contamination. It will prevent contamination from sticking on the stem surface. So this is the kind of last slide. Okay, so we need to control molding temperature, pressure, and time. Okay, so this curve shows typical specific volume versus temperature for, in this case, the amorphous polystyrene, but that applies for most of polymers. Okay, so now here where the slope is changing, this part is TG. And they show at different pressure. Okay, so now let's just try to follow the nano imprint process or hot embossing process. What do we do? So we start from the room temperature, we increase the temperature. Okay, and then we increase temperature above TG of the polymer. And then what we are doing? We apply pressure, right? We apply pressure. Either, depending on the pressure applied, either 50 millipascal or 100 millipascal or something like this. And then, let's say we apply 50 millipascal. And then we cool down. And then now we cool down below TG. And then we demold. Okay? So now let's think about how temperature, pressure, temperature, time will affect. The first one, the pressure. I think a lot of people think, oh, we can just increase the pressure to feel better. But what happens? If you increase the pressure, okay, TG increases. So now, if you increase the pressure up to this point, what happens? Your polymer is not anymore above TG. So molding is more difficult. So you cannot just increase the pressure a lot. Of course, if pressure is not enough, then the filling, you have trouble in filling. Okay, how about temperature? Okay, again, if temperature is too low, then your polymer is not mobile enough. But if you increase the temperature too high, then what happens? There will be a lot of thermal stress generated during cooling process. So your substrate can be warmed. There's a deformation. So this is not good. So also you need to control the temperature as well. And time, again, if it's too short, not enough time to fill. But if you increase the temperature too high, then what happens is polymer chain will align along the substrate. Then it becomes crystallized. Okay, then it's more difficult to fill. Okay, so bottom line is for each process, you have to really optimize pressure, temperature, time, so that you can have like an optimal molding process. I think that's all I have. Any questions? Yes.
So, Professor Park, what about gases? So, if you're doing this at atmospheric pressure, there's polymers filling the mold with hot embossing injection. What does all that trapped gas do?
Yeah.
Into the polymer? Do you evacuate out the chain?
I would say for nanoscale molding, the gas trapping is not very important because the amount of gas is not a lot. So most of some gas can dissolve into polymers, and that is what happens. But if you have like huge structures, like huge microstructures, then I think the gas trapping is a more significant issue. So I think, for example, the hex machine use vacuum, right? So and so basically, before you press, I think they pull vacuum in the environment, so that the gas trapping is kind of less significant. But okay, for nano molding, we didn't have any problem. Any other questions? Yes. It's very, yeah. There are three, when I did my PhD, we already made it so. There are three things you cannot trust. First one is the temperature. So, even though you read temperature from papers, you cannot really trust. Okay, so you cannot really trust temperature. And then the second one is thickness. Even though they report, oh, the thickness of our layer is what, you cannot trust. Right, thickness can never be the uniform. Always there's a variation, and also it depends on, the homogeneity of your film. You know what is the third one? Is operators. So this means you have to really work and determine the parameters for yourself. Do not, again, all the values from the literature can be guide, okay? But you have to really determine all the process by yourself. That is a little bit difficult for many chemist students who work on this micro and nanofluidics, because they are not really spending a lot of time in manufacturing, okay? They try to just get the parameters and they want to produce easily, and so that you can more focus on analysis part. Okay? But if you really are involved in engineering area, I think you have to really spend some time to optimize your process for making structures. Any other questions?
So I just want to add that parameters may be optimized, but it also might heavily depend on the substrate, right? And then from vendors to vendors, thermoplastics may contain different amount of plasticizers, for example. So it's not that the reported temperature, pressure, time are not valid. They're valid for this